and brightness of this room? Good question. Is this just how the UK looks like? Where's the sun? Thank you. Oh, it's so grim.
We delayed just long enough.
You aren't with me yet.
Okay. Oh, look, I got a nice piece of chalk. Whoever brought me that, thank you very much. Right. So, continuing, I'm gonna, I want to continue to tell the story. I'm going to sort of, I'm going to make a couple of moves that I'm not going to fully motivate just in the interest of time. Because I want to make sure that we still have enough time to have like a full conversation about these things. So I want to, I'm going to make a couple of unexpected kind of left turns in places, and it'll be okay. So that's what I want to say. So where were we? So what we did is we talked first about how it is that when you think about opens in a topos, that allows you to sort of decompose your topos into sort of constituent pieces, and then you can re-glue your topos from those constituent pieces plus gluing information. So, and that was the situation of the recollement, right? So the situation was, well, you had sort of an open and a closed, and the open was in, there's actually two embeddings of the open into the whole thing. J upper star between them, and then in this other direction we had I lower star. And this is a recollement type situation that we were for topoi. And one of the things that I want to emphasize is that you can always just write down an example of this and sort of play with it if you like by doing the following thing. You could look at functors from this category into the category of anima or whatever. And well, inside here, what can you look at? You can look at functors, well, out of one, right? So this is just another name for spaces, but it's a suggestive name for spaces. And here's another suggestive name for spaces. Should call it 0, yeah. And well, if you think about the behavior of things like left and right con extension, then you see that this is actually a recollement of these two in this way, where this is the open piece and this is the closed piece. So these are, this is the restriction, these are left and right con extension, and I have these two functors here. In fact, I actually also have the third one in this case, but I'm not going to draw it because we don't want to mislead you into thinking that we get it all the time with topol. So, all right, if you think about this, then, in some sense, what this is telling you is that in this sort of recollement type situation, well, what can we do? We have this sort of open piece, which is kind of controlled by the sort of, this bit is open and this bit is closed. If you think about algebraic geometry very much, then you might think, oh, that's kind of like spec of a DVR. When you think about the Zariski topological space of spec of a DVR, there's only 2 points. There's the open point and the closed point, right? And one is in the closure of the other. So, and this is that arrangement, right? In fact, this is actually sheaves on that topological space, on this topological space. So anytime you have a poset, you can give it a topology. You don't normally think about this topology if you're a theorist, but it's a perfectly valid topology called the Alexandrov topology. And then an open in here is the same thing. Well, the terminology gets stupid. It's an upwardly closed subset. I don't like using the word closed when I'm talking about topology, especially when I'm defining the opens. But so like if and only if for every x and y in P, if x is less than or equal to y, and X is in U, then Y is in U. So it's upwardly closed. Right? Those are the opens in the Alexandrov topology. This is usually, we normally, as if you're the kind of homotopy theorist that sort of starts with CW complexes and moves on from there, then you tend to think of these kinds of topological spaces as the sort of things you prefer to avoid at all costs. These things are non-Hausdorff as soon as the poset's interesting, you know. You're supposed to avoid these things, is what I'm trying to say. However, Lucas in his talk told us that, well, you're actually not supposed to forget about these things, because if you have a topological space X and you want to talk about stratifying it, then a compact way to describe a stratification on that topological space is to define it as a continuous map down to your poset, where you think of this as equipped with the Alexandrov topology. So for example, if I write down a map from X to this dinky poset, then, well, what am I doing? I'm decomposing X into an open piece and a closed piece. In the same way, if you have a recoulement like this, you can always construct a morphism of topoi. In fact, a unique morphism of topoi with the property that this is the thing that you get over 1, and this is the thing that you get over 0, so that these are pullbacks in the category of topoi. In other words, what am I telling you? I'm telling you that Lucas's definition of a stratification of a topological space over a poset is going to work perfectly fine even for topoi. Namely, I'm going to do the following thing. If I've got a poset, I'm going to define P tilde be the topos functors from P into N. And here's the definition, a P stratified topos is a morphism of topoi from X to that poset. Oh, but I'm going to put a tilde over it now. The topos now. Remember, morphism of topoi, what does that mean? That means that, well, there's a P lower star, which is a functor, and it has a left exact left adjoint P upper star. And then when you have an open inside this poset P relative to the Alexandrov topology, you can pull it back. And when you pull it back, you get an open subtopos of X. So you really are splicing up this topos according to this poset. I feel like we're quieter than usual. We were more talkative yesterday. Are you all tired? Is that the situation?
Is this the same as sheaves on the topological space?
Yeah, it's the same as sheaves on the topological space, the Alexandrov topological space. That's right.
He identifies with the lattice of opens up.
Yeah, well, at least if your poset is finite. And that's the sort of situation I'm going to be concentrating on. So, yeah, I mean, what do I have to say in general? Noetherian or something?
Theory is sufficient, but
It is sufficient.
yeah, if it's infinite, it's always hypersheaves.
It's always hypersheaves. Thanks. Yeah, right. Right. In general, you might not have, the topos might not have enough points. So,
Sorry, then if I could have asked some really dumb questions.
yes, thank you. Finally. All right, let's go.
Here, it's poset still has lots of opens, right? So when you say,
Wait, this one here, this one doesn't have so many.
that's why I guess I was misunderstanding the definition. So aren't the intervals that are,
So this set has 2 elements.
oh, it's just 2 elements. Okay, that's what I misunderstood. It's just 2 elements.
Sorry, yeah, no, I'm not talking about the interval from 0 to 1. I mean,
Okay, yeah.
the 2 element set regarded as a poset where one of them is less than the other. Yeah.
Good that I asked you. Yeah, right, very good.
Yeah. It's no intervals have appeared. Yeah, no.
Okay. So
Yeah.
then in this definition, so P was the poset.
Yeah.
And P tilde is also a poset then, I guess?
P tilde is a topos, yeah,
Right, but then you said P, so this is a map of
of topoi.
topoi. So, so P tilde is not a poset, right? Yeah, that's just a topo.
No, P tilde is the topos attached to the poset.
Oh, yeah, no, I understand. So then you're saying this morphism is the same as having a P stratified topos, so one of these things. Right?
Well, I'm saying that this is the definition of a P stratified topos.
Right.
Giving a definition. I was using Lucas's definition. Yeah, I don't know if you're
No, no, it wasn't.
but he gave a definition of what it is to be a P stratified topological space, which is that you've got your topological space and you map down to P with the Alexandrov topology.
Okay, yeah, I think I understand this now.
And so this is supposed to be the analog of that. And the example that I gave to sort of try to influence or to suggest that that was a really good thing to do was the example of this boring poset, this 2-element poset. And if I map X to that boring poset, then it automatically gives you a Coleman.
Yeah, okay, I see. I think I understand.
Thank you for making me say this better. It gives you a Coleman. So it really does feel the way stratifications feel in topology, this open closed decomposition. Yeah.
You said something about this map. Is this, yeah, so what is the sort of universal property? Did you say that you get U and V as pullbacks or did like,
Yeah. So this is a, like this J lower star. So how did I do that? So if I think of this I lower star and this J lower star, these are morphisms of topoi. Right? So let me actually, I mean, this is what a Coleman is, but let me take out the fluff for a second, just so you can just see the core structure. So I'm just going to draw the morphisms of topoi and all the adjunctions are going to be implicit. So I'm going to have this morphism of topoi, which is open. And I'm going to have this morphism of topoi, which is closed. And if I have a map, a morphism of topoi down to this, then I can form the pullback in topoi. And that will automatically be an open subtopos of X. And I can do it on the other side and get a closed subtopos of X. And these form a Recolement.
and moreover, every Coleman arises in this.
And moreover, every Recolement arises from such a construction. In a unique way. It's a equivalence of categories. Yeah.
If X is like a topological space, do all like stratifications of its sheaf topos arise from like actual stratifications of the topological space?
Yes, provided that we're talking about finite stratifications or that we're careful about this hypercompleteness business, yes.
Maybe sober.
Do I have to say sober for this?
You should say so.
But the,
You don't. I don't. Yeah.
let me just be
Nice.
edge with sober, just to be careful.
Just in the left square, is it the streak or star that we're taking the pullbacks out? Like
The stars,
we had to,
the
yeah.
stars are the ones that are the,
It-
yeah, that's right, thank you. And that's not the pullback in categories. It's the pullback in topoi, which is, they're different.
It's useful to say also what the object you're slicing over in your description is. So if, like the geometric morphism is say P lower star,
Here, yeah.
then you're slicing over P upper star of the sheaf associated to element 1.
Yeah, so how do I denote that sheaf?
Yeah, I don't.
I'm just gonna write 1, but 1 means, that makes it look like the terminal object.
1. I don't know.
No upper 1 or something, is that what?
Yeah, yeah.
So this is a description of the pullback and
This is a description of that pullback, and it's a slice category, and this obviously needs to be a slice category over something that's -1 truncated. And the claim is that you take the pullback of the sheaf represented by the number 1. Siri just started recording whatever it is I said, so that'll be exciting.
I had another question. So
Yes.
these function categories or topoi, are they in like the category hidden categories or like how should I, or
Yeah, these are functors of infinity categories, but what is this category, right? It's really just the category of arrows in the category of spaces. So it's not a, yeah, it's not too fancy.
It's the space of spaces that are stratified over 0, 1, is that correct? Or like, not quite? Well, I guess not quite. Right?
No, so this isn't the category of spaces that are stratified over 0, 1. This is a, how should I say this? I have something smarter to say than just that it's the functor category. I don't think I have something more intuitively appealing. So well, okay, I mean, I do sort of. It's you can also, this is pursuant to the point that one of you made, is that this is also the category of sheaves on this topological space, this with the Alexandrov topology. And maybe here I have to, well, no, okay, it's okay. Is that, are we buying that? Is that, we're happy? Okay.
I was trying to do a Groton deconstruction, but I think it doesn't work somehow.
I might have something to say about that, but I will get distracted if I try and say it. So let me not try to get, I have to try and stay a little bit focused. Doesn't
Just one last elementary clarification.
Please.
Just make sure I'm not really confused. So what you said is that P tilde is the topos of P, right?
Yeah.
Okay, I see, I understand. And therefore, having a map of this sort is the same as having a map from X to P. Okay, yeah, that's what I was.
Exactly. Yeah. Yeah. If this thing comes from a topological space. Yeah. 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 Exactly. Yeah. Right on. Let me show you how this comes up in algebraic geometry. So suppose that we start thinking about stratifications of a scheme. And actually, maybe I really just want to focus on one scheme right now. I'm going to focus on spec Z. Love spec Z. Always there for me. All right, so if I think about spec Z, then what I learned in school is that I've got one generic point, which I'm supposed to kind of draw in a fuzzy sort of fat way, which corresponds to the prime ideal 0. And then for every prime number, I have a little ideal, which is, these are all closed points now, right? Let's see, 5 is next, isn't it? Okay, and that goes on. And well, this is the usual picture. This isn't really showing you so much about the topology, and it's never been quite clear to me why you should think of this thing as linearly ordered. I mean, it's one dimensional, like in terms of curl dimension, but that isn't such a deep thing. I prefer the following kind of picture a little better. I prefer to think of it like, if you think of 0 here, like if I close this point up, I'm going to get everything, right? It's the generic points. That means that these little points here, they're actually like barnacles stuck to this thing, right? And there's 2 and there's 3, and if I had more colors, yeah. And there's 5, and they go around like that. Right? That's really what it feels like as a topological space. Right? Topological spaces are not all there are to schemes, but if I was just thinking about the Zariski topological space of this scheme, it sort of feels more like that. Right? And maybe I'll just mention one more thing here, which is that the way the topology works, you can only keep finitely many of these closed points in focus at any time. You can keep an arbitrarily high number of them in focus, but it has to be a finite number in focus. That's how the topology kind of, focus means you've got a closed subset, you know what I mean? So yeah. So this is what it's like to be on the Zariski topological space of spec Z. And now, so this topology, where does it come from? How are we supposed to think about it? And well, the thing is, right, these little points here, they're kind of, they're contained in the closure of the big point. So that means that they sort of have like, they have a relationship. You can kind of think of this point as less than or equal to this point. Sort of in this kind of Alexandrov-y kind of way. So it's almost like the Alexandrov topology of a poset. I said this thing about only being able to keep finitely many of them in focus at any time, right? It's not just an Alexandrov topology, but it's something really close. In fact, what it is it's a pro-finite poset. This thing is a pro-finite poset. Namely, what can I do? Well, I can imagine the circumstance where you have only finitely many of these in focus, which is to say that you've pushed the other points into the big point, let them join the bulk. And then you sort of refine by adding more and more points. That gives you a big inverse system. If you take the limit of that inverse system, well, then you can get a pro-finite poset. But if you take that limit in the category of topological spaces, you exactly get this Zariski topological space. And this is true generically for schemes. As long as your scheme is quasi-compact and quasi-separated, and why are you thinking about non-quasi-compact schemes? As long as your scheme is quasi-compact and quasi-separated, its spec as a Zariski topological space is actually a pro-finite poset. That's precisely what it is. So maybe I'll just say this, which I guess is sort of in Hochster's thesis. I think this is sort of a digested version of some of the things in Hochster's thesis.
Is this commutative algebraized Hochster?
Yeah, Mel Hochster.
That's been a while ago.
Yeah, this is 69 or something. Yeah. This is old stuff. None of this is new. Everybody's known this for years. Except no one ever says it out loud that this thing is just a big fancy poset. Like no one ever admitted that to me, and I didn't even know it until recently.
Was he the person who showed that spectral topological space is spec of a ring?
Yeah.
Okay, well.
Yeah, okay, so. So there is a particular kind of topological space called a spectral topological space.
And this is that from the Midwest. Where does he work, Clark? You
Michigan. You
Michigan. So as a spectral, we can talk about spectral topological spaces. I'll just tell you in words what these are, and if you have questions, I'll answer them. So these are quasi-compact, quasi-separated, sober spaces, such that there is a base for the topology given by quasi-compact opens. Quasi-compact opens. Now, if you were in a Hausdorff situation, if I included the adjective Hausdorff instead of the adjective sober, then saying that I have a base of quasi-compact opens is saying that I have a base of clopens, right? Which tells me that I'm totally disconnected. So I would, if I'd said Hausdorff there, I would have given you a description of stone spaces. That's what those things are called, which are pro-finite sets, as you might know. I'm now saying, okay, well, I'm going to lose the Hausdorff but keep sobriety instead. And when I do that, I don't get a pro-finite set, I get a pro-finite poset. And that's the statement here. Pro-finite poset. By the way, the maps that you have to take here, they need to be quasi-compact maps. Can't just be all continuous maps. You need to take quasi-compact maps, and those correspond to pro-finite posets here. It's a map such that the pre-image of a quasi-compact open is quasi-compact. At least in this category, that's the correct definition. I have to do something to, never mind. Anyway, there is this sort of constant risk to just sort of fall off the cliff into general topology, and I'm trying to sort of stay on just the right side of this, but we'll see if I end up falling off. Maybe I'll just say what Piotr just told us, which is that these are also those topological spaces. I'm just going to say this really roughly. Those topological spaces of the form spec A, SAR. The Zariski topological space of your favorite spec A. This is, I'm not telling you that this includes the maps, right? I'm not saying that. I'm just saying that if you look at the full subcategory of topological spaces and quasi-compact continuous maps spanned by topological spaces that can be written as spec A ZAR, this is that. way in which you show that every spectral topological space can be written as spec Azar is you got to build an A, and the constructions. I only know crazy constructions. You probably know a sensible construction though, don't you?
I don't actually.
Okay.
I
He doesn't know a sensible construction, so that's
my algebraic geometry student, they had to do a end of semester project, and a bunch of them chose to write expositions on Hofstadter's thing.
oh cool.
So he does show that if you fix any two spectral spaces in a quasi-compact map, you can find rings and a ring homomorphism
Right.
that induces this, but it's not functorial. It's just like you can do that individually.
So what about the non-affine scheme?
Yeah, what about a non-affine scheme? It turns out it's the same thing. Zar of a QCQS scheme.
So it's a moderate.
Well, it's just because the topology is just very, very forgetful, right? I mean, it really doesn't know that much about the scheme, right? I mean, all curves over a field are homeomorphic. Complete connected curves over a field are homeomorphic. I don't need to say complete. It's just, there's
There's a number of these amusing theorems about the class of varieties that are determined by their Zariski topology, right?
yeah,
That's a bit.
Yeah.
it's which they're surprising theorems.
I guess that also kind of eliminates properties of rings that you can guarantee. Like if you're, one of these varieties that's nice enough of big enough dimension that's determined by its Zariski space.
Yeah.
The ring can't be some nice thing. Otherwise it would contradict this type of theorem.
Oh, interesting.
So you can only find a terrible ring.
You can only find terrible. Oh, that's good. I like that. That's a good principle. Right, because all those. Anyway, okay. I have questions about that, but I'll come back to it. Okay, so what does that mean? Why am I talking about this? Well, I'm going to sort of examine. So we had this story for topological spaces. Thank you, Lucas. And then we had this story for topoi. We can now stratify topoi using basically exactly the same recipe. And then what I'm saying here is that I can even start to push this a little bit. I can start to take P here and let it be a little more than just a poset. I could even let it be a profinite poset or equivalently a spectral topological space. And if I do that and I take sheaves, let's see, let me actually write something down that's cogent. Got a board over here, don't I? All right, so let me write down here something, which is that. Suppose that I write down a spectral topological space and I construct it as a limit of some finite Alexandrov spaces, right? So I take these finite posets, I write X as a limit of those finite posets. And this is a nice topological space. And then I ask what sheaves on that nice topological space look like. So now this is like Zar of something, right? This is the Zariski space attached to some scheme. And so, well, sheaves on this thing are something that these are just Zariski sheaves. And it's the limit of these P alpha tildes in the category of topoi. The limit just passes right through this sheaf construction. So what does that mean? That means that now I'm permitted to talk about stratifications, not just over posets, but in fact over profinite posets. Why would anyone ever do this? Well, perhaps they have a scheme. So if X is, well, let's see, X is too many things. So if Y is a scheme, well, then what can we do? We can look at this Étale topos, which I briefly mentioned and then abandoned. So let me come back and rescue. I have this beautiful Étale topos. And that has a map to the Zariski topos. This is sheaves on the Zariski site. So I'm going to assume my scheme is, this will happen. This is a permanent thing. All my schemes are going to be quasi-compact, quasi-separated now and forever. Okay, so I can talk about the Étale topos of that scheme as stratified over that profinite poset. So, all right, so now I've concluded that in fact, the whole business with the Zariski topology, those are really just glorified posets. And I can stratify over them the same way I stratify topoi over finite posets. And the Atoll topos is an example of such a thing. So now we get to ask a fun question, which is, well, here's spec Z czar. That's what it looks like. I'm going to erase the older fashioned picture. Right, it's a poset, but it's sort of pro-finite because of this business that I can only keep finitely many of these and focus them. And well, the Atoll topos is something that lives over this thing. So we get to ask a fun question, which is, well, what does this Atoll topos look like? How can we do it? Well, it's some sort of stratified topos. All right, well, the story with our recollement is that if you have a recollement, then you can reconstruct the topos from the open piece and the closed piece along with some gluing information. Right? We concluded that that was the situation. So the same kind of thing is true here. Namely, if you've got a stratified topos, let's say to start off with just over a finite poset, then you can reconstruct the whole thing from the information of the strata and how those strata fit together. In the languages of Lucas's talk, that means that we're talking about the strata and we're also talking about links, which you can think of as exit paths that go from one stratum to another. The space of those exit paths are what I mean by the links. So if I want to understand this thing here, then what I want to do is I want to understand the strata and I want to understand the links. Okay, well, let's think about it. So how did the strata work? Well, I've got a couple of different options, right? Either I'm looking at one of these closed points or I'm looking at this open point and I'm looking at the fibers over it. And I'm trying to understand what kind of topos I'm looking at. Everybody happy? All right, yes.
Can I just a sort of language question?
Yeah.
Should I still refer to this as a stratified topos or like a profinitely stratified topos?
Just call it stratified. As soon as you say that it's stratified over something that's profinite as a poset, then I don't think there's any room for ambiguity about what you mean. You'll be safe if you say that. Okay, so what do I have to do here? I have to try to understand what this topos looks like. And I'm going to do that by trying to understand all the strata and how they fit together. Okay, so the strata, what do they look like? Well, I've got these points here. And if you think about it, if I look at the stratum over P, well, then what's that going to look like? Well, it's going to look like the Atoll topos of spec of FP. Okay, well, let's think about that Atoll topos of spec of FP. We talked about it a little last time. I kept calling it, I talked about locally constant sheaves on spec of a field, but I'm talking about spec of a field here, right? So, I mean, they're, in the presence of some finiteness, they're automatically locally constant. I guess it depends on what you mean by locally constant. Sometimes local constancy, or when you talk about a local system, you mean to include some finiteness conditions, but let me just skip that for the moment. I need to understand what this is. And the answer is the following. It's spaces equipped with a continuous action of the absolute Galois group. So it's spaces. I'm going to write it this way because I want to emphasize the analogy. So I'm going to take the absolute Galois group of FP, which is a profinite group. And I want to look at spaces with a continuous action of that group. Now we still have an issue, right? I haven't told you what this CTS business is all about. How am I going to make that precise? Let's put a pin in that. I'm going to come back to it, but I do need to address that issue. But let's just let's feel it out for a minute here. So what is the absolute Galois group of FP? Mignon doesn't answer this. absolute Galois group of FP?
Something or no?
No, it's easier. What kinds of extensions can I do for an FP?
It's like all finite integers. Or...
Yeah, it's the profinite integers. Yeah. I can only do cyclotomic extensions. That's all I can do. And so I end up with Z hat. So this is the classifying space of Z hat. This is the classifying space of Z hat. So it's kind of a profinite circle. I mean, it's literally a profinite circle. It's actually not kind of a it's literally a profinite circle. I don't know why I'm being coy about it. It's literally a profinite circle. So it's literally a profinite circle. So when I think about this stratum, this spec FP stratum, what I should be thinking about is a circle that's embedded as a closed in whatever this thing is. Right? It's one of my strata. It's a closed stratum because it's a fiber over a closed point. And so I've got this circle that's embedded in here. So I've got this ambient space, whatever it is, and I've got this embedded circle that sits inside there. And I've got one of these for every prime. Okay. So I've got this space and I've got this embedded circle. I probably need to understand something non-trivial about the space in which it's embedded.
How am I supposed to understand the profiniteness when I think about this as like a circle?
Yeah, good question. No, so I'm just being a jerk. This what you're able to do is you're able to take any anima and profinitely complete it, and that's what we're doing. There is actually a smaller thing than this called the V group, which in this case is just Z. It just powers the Frobenius. And that thing actually gives you a proper BZ. So it's like a true circle that you could think about. But that's not just something that comes from the Étale topology. It comes from something a little bit more than the Étale topology. And while it's not mysterious here, it becomes increasingly mysterious as you pass out to this thing. So out here, there's a V group too, but I super don't understand it. I think number theorists do, but I don't. Yes.
In what sense is the spec FP et al. Embedded into spec Z et al.?
It's a closed subtopos of this thing. And its complement is spec of Z brackets 1 over P et al. Right, invert the
There's like a recoulement.
is a recoulement, exactly. So this is closed, and then there's the open complement, which comes from the open complement at the level of schemes.
But the closed thing would be something like that. It's not quite sheaves on the closed thing, but like sheaves supported on the closed thing, or so like some kind of complete thing maybe, or in this case it's this.
In this case, it's this, but you're getting at something that's very important, and it's a distinct difference between the geometry that I'm sort of pulling us towards here and the way we normally talk about the geometry of stable infinity categories.
This was like Fuko or something, then
You're gonna make me talk about this.
I was just
So what is the continuous here? Like this is not functors of infinity categories.
Yeah, that's right. There's an extra layer of continuity that's required here. I can give you a sort of ad hoc definition for now, and then we can explore more like what the meaning of this definition is. But you can write this thing down as the limit over n of actual functors bz over n into anima. Yeah.
Way I thought was that you have like continuous maps because I guess like for Z hat you have the Frobenius as like a topological generator.
Yeah.
So like, is there a way to think of like the Frobenius like acting on the poise? Like what's
Yeah.
how would you visualize that?
How would I would visualize it just by moving around the circle. But maybe that's not what you're asking. Maybe you want to. I mean, yeah, the Frobenius is literally the generator that goes around that circle. And I mean, when you say Frobenius, do you mean the geometric Frobenius or the arithmetic Frobenius? One of these is inverse to the other, right? And so that's a kind of a choice of an orientation on that circle,
Okay.
right? Because you're choosing a generator of the Z. If you know what I'm talking about.
Yeah.
Is that okay? Yeah.
good question. How does a pullback?
That's a great question. In general, I don't have a superb answer for you. I actually, Peter and I have been talking about this just recently. I like, in general, I don't know how to write down. Well, that's not true. I can give you a site in many cases, but I mean, in general, it's a nightmare. In the case of open subtopoi, you can give an explicit, it's this sort of game that Peter was describing here. If you've got an open subtopos and you're doing the pullback,
Sliced open.
like if I'm doing a pullback like this, so this is an open thing, so I better call it J, otherwise I'll be banished from the club. Then this thing, if this is open, that means that it's X prime sliced over something that I'll call U. And if this is, I don't know, I've really not thought through the notation here. So if I'm performing this pullback, then this thing is X sliced over P upper star of this U here. And that is the pullback in topoi. So I can tell you what the answer is in the case where you're pulling back along an open immersion or more generally an automorphism. But in general, I mean, I just know that it's there. And I can sometimes write down a hideous looking site that will give you what, what it's, you know, that will give you that topos. But I don't, do you have something better to say, Peter? It's
Maybe just highlight that also for a closed immersion, this tells you what it is, because it's the complement of P upper star U.
yeah, thank you very much. Yeah, so if you've got a closed, if you're looking at the closed thing down here, thank you. If you're looking at the closed thing down here, then the complement, then the pullback is actually going to be the appropriate complement of P upper star of U. So it really is going to break up the way you want it to.
So in this case, to get the strata over P, we're looking at the sort of pullback over the complement of P in the, like, I guess I'm trying to figure out what the strata over P means in this case.
Right, so it means, so P, so spec of FP, so spec of FP, czar is exceptionally boring. It's a point, and it is being included in here as a closed at P. And I'm performing the pullback in the category of topoi, and I'm getting spec of FP bar. Or sorry, not F, ignore the bar part. The rest is right. Spec of FP at.
And that is the X prime over U for U, the complement of the prime ideal.
Oh, yeah, so right. So where's the open in this? Well, the open is spec of Z brackets 1 over P.
Okay.
Right. So if I look over here, I can look at spec of Z brackets 1 over P czar. And that's an open sitting inside here. And if I pull that back, well, then I'm looking at that at the atoll topos of this thing. I don't, I mean, I'm going to have to do some more work to tell you what that is.
Could I ask a question about this continuous business?
Yeah.
First, this limit is a co-limit, I guess, is that it?
This limit is a limit.
It's a limit?
This limit is a limit, and it's a limit along the
The map from Z hat maps to Z mod n. So
that's right.
it's the limit of the Z mod n.
Yeah.
So
And then
the is going the opposite direction.
that's, but those are the upper stars, and I'm doing the lower stars. So, right, so Z mod n. If Z mod n maps to Z mod m, oh God. All right, fine, I can do it. Then I have a right con extension. And that's the functor that I'm using
Oh, I see.
when I perform this. Thank you for making me say that out loud. So this is the lower star, not the upper star.
Okay.
And I'm taking the limit along those things.
I see.
So that means that an object of this category is a compatible system, but the compatibility is with P lower star. So I've got like a functor here, and an equivalence between P lower star of this functor and that functor. So you see how it works.
Actually, this may be answering my question, which was, I was thinking about the co-limit, in fact, and then in the usual treatment of étale sheaves, co-limit thing usually works well only when AN is the sheaf itself is finite.
That's right, exactly. That's
But
precisely.
This is sort of taking care of all that.
Yeah,
This is taken care of.
also true that, yeah, if you, well, sorry, I should not.
No, please.
Yeah, if you restrict to the finite guys, then you can replace it by the column.
Oh, I see.
Yeah.
I didn't know this at all. Very,
Yeah.
very nice. Yeah.
Other questions? Yeah.
Sorry, you might have said this, but so opens always pull back to opens and closes?
Opens always pull back to opens, close always pull back to closed. Yeah.
So it seems if I have any scheme and I take like the pullback of like the Zariski side of that scheme to the Zariski side of Z and the etat side of Z,
Yeah.
you always get the etat side of the scheme.
Yeah. Yeah. Life's good that way. Yeah. It worked perfectly. Yeah. Yeah. It works just the way you want it to. Yeah. Good things happen almost all the time. Okay. So, I want to understand this further. I have an issue here with this continuity, right? I need to figure out what I mean by that. We're going to have to get to the bottom of that sooner or later. I will get to the bottom of that sooner or later. I swear. But I also want to think about, I still have this big, it's not open, but I have this big kind of pro-open stratum, like it's an infinite intersection of opens, right? Which is sort of the pre-image over this big point here. Well, what is that? That's going to be the Étale topos of spec Q. Right? Which means that I'm going to be looking at continuous functions from the absolute Galois group of Q, from B of the absolute Galois group of Q into spaces. So what is the absolute Galois group of Q? Okay, good. So you realize that was a joke. Good, thank you. No one knows, so it's a big mystery. But we do know stuff about it. Namely, we kind of know how its cohomology behaves. And that's going to be enough for me to be able to draw a picture here. So this part of the story, we're going to have to black box just because like I could give 4 lectures just about this, but it's 3-dimensional. So I want to draw this diagram again. So it turns out, and again, I really don't have time to justify this, but when you look at, this is the Zariski space, and then when you look at the Étale topology, what it looks like is a big 3-dimensional thing. And embedded in that 3-dimensional thing, for every prime number, you've got a knot embedded therein, corresponding to that circle. And I can't draw a knot, so I'm just going to draw the unknot. Don't care. It's fine. So I have to tell you, so these things are genuine knots in the sense that they're embedded as closed subtopoi, and they are themselves as close to S1s as our profinite brains will allow.
This should also have a barnacle shape somehow.
Pardon?
The knots should also be barnacles.
Well, like in some sense, the way I think of this, you also have intuitions about this, of course, so you can tell me what yours are. But my intuition about this is that when you think about spec Z through the Zariski topology, that you've taken your binoculars and you've made them really, really fuzzy, just so you can get the sort of general shape of things. And what you see is this sort of general kind of, you see that this is sitting inside as a closed of this whole thing. And then there's this big complement thing here. And like all you know is this sort of very structural facts about spec Z. And then here, this is sort of a much more, you've changed the resolution on your binoculars, and now you can see much more finely. And you see that this is a 3-dimensional thing with this embedded knot. But this knot is embedded as a closed in the same way that this point here is closed inside this whole thing. The open thing is the complement of all the knots.
Okay, I see.
Or not open, but pro-open. Is the complement of all these knots. There's infinitely many of these knots. You can only keep finitely many of them in focus at any time. And they're actually all secretly profinite. So there's this kind of weird kind of profiniteness that's happening in the bottom of this. So, okay, but I said that in order to really understand this, you have to understand not only the strata, but you also have to understand how they're glued together. Well, we didn't finished understanding the strata because we still don't know what the absolute Galois group of Q is. And even if we did, could I draw a picture of it? I don't think so. But I can try to think about how this thing is glued into this entire space. Right? That is to say, I can think about a tiny little neighborhood around that closed point so that I'll picture how this knot is embedded in this space. So I'm going to think about a tiny tubular neighborhood around that knot. And then I'm going to think about taking the original knot out of that thing. And that's going to give me something that I want to imagine as a knotted torus sitting inside here. That corresponds to spec of QP. So I can't draw knotted tori any better than I can draw knots, certainly. So you have to work with me on this. And they're not really toruses because there's no orientability here. So these things are like Klein bottles, but they're not even that because it gets worse. But that's sort of the picture that we're having. The way the atoll topos of spec Z looks. That's what it's like to hang out in it. By the way, where do these things come from? Where do these facts come from? These statements about how the thing looks, this three-dimensionality and this two-dimensionality. The two-dimensionality follows from a sort of a two-dimensional Poincare duality called local class field. Well, local class field theory has more than just this Poincare duality statement, but it includes the Poincare duality statement. And then global class field theory is where you get this three-dimensional structure from. Yeah.
So you've drawn a link there.
I've drawn I've drawn a deleted tubular neighborhood of the knot inside the thing.
Yeah.
And that's supposed to correspond to spec of QP.
Right. So I guess in the geometric setting, I can give you like the middle phase of constructing the homotopy, like depending on what my face has or doesn't have.
Yeah.
How do I get it from a topos?
Right. So where is the link? If I've got this, so let's suppose that I'm looking at a situation where I'm looking at topos over. Let me just do this with just a post set here to start off with, and then it'll work the same in general. And so suppose that I'm interested in two different strata, which is what I am interested in, right? I'm interested in this closed stratum, and I'm interested in the bulk, right? So I'm interested in two different strata, so that corresponds to a map from here into here. Now I'm representing it as a map of topoi, but it just comes from a map of post sets that's picking out 2 points of my post set, one smaller than the other. And I'm interested in trying to write down the space of all the paths that go from the 0th thing to the first thing. And what that is it's the space of all of these sections that make this thing. So it's exactly the same as what happens when you think about these things as layered infinity categories.
No.
You had a brief moment of I'm going to say this thing, but no. Okay, so I have to stop, don't I? Let's stop. Okay. So this is the study of this picture and its meaning for all of us is the thing that's called arithmetic topology. And you can start to try to, so right now, as I'm telling you this story, what I'm giving you is a picture of this thing as a stratified topos. But in fact, there's going to be a claim that I'm not going to be able to make today, but the claim is going to be that it actually corresponds to a profinite stratified space.
What corresponds?
The stratified topos. So this spec Z atoll here is actually itself a functor category, but I have to say continuous functors. And then here I have to write something new, and it's going to be a profinite stratified space that we call Gal of Z. Because it incorporates all of the absolute Galois groups of all of the residue fields and all of the sort of ways in which they're glued together in a single stratified space. And you're looking at continuous functors from that into spaces. So in fact, the atoll topos is actually itself a functor category once you figure out what you mean by continuous functors. And I'll sort of say more about that next time. And this is going to be part of the exogamy theorem. And then I will also, I promise, explain why this QCO business feels so different. But there's a very good explanation for it, I claim. So I want to talk about that. Okay, thank you.